In this video, we'll explain the key differences between EDEM's three main bond models. We'll focus on failure type, moment resistance, damping, and other key parameters for each model. Before we start, let's have a quick introduction to each of the bond models. First, the bonding V2 model. This is a general-purpose model used to create flexible bonds between particles, and it's particularly useful for modeling rock structures. To allow particles to bond, you must add a contact radius. This model is most commonly used with multisphere particles. Next, the linear elastic bonding model. This model defines elastic bonds between elements that cannot break in the normal direction under compression. This results in a more elastic behavior, and the model supports all particle shapes, including polyhedral particles. Finally, the fibers bonding model. This model keeps particles bonded together to simulate long and flexible structures like fibers, branches, or strings. Let's start with bond location. For the bonding V2 and linear elastic bonding models, particles are bonded at their contact points between spherical elements. These models are mainly used for non-elongated structures. If you try to use them for elongated shapes, you might see what's known as the raspberry-like effect. However, the fibers bonding model has been designed for elongated structures using spherocylinder particles, such as fibers. Unlike the other two models, it allows you to bond particles at different locations, not just at the surface. Next, moment resistance. The bonding V2 and fibers model both exhibit bending resistance, making them suitable for beam-like behavior. However, the linear elastic bonding model does not include moment resistance. The only way to achieve bending resistance with this model is by using a clump of particles. Next, failure types. For the bonding V2 model, the bond can break under tension, shear, or torsion once the defined bond parameters are exceeded. The linear elastic bonding model only fails due to normal or shear forces, not twisting. Finally, the fibers bonding model can show different failure behaviors from buckling to complete breakage, depending on the input parameters used in the model. This model features multiple failure options, including bending-caused stress, bending angle, axial stress, stress from forces, and general-purpose von Mises stress. Next, we'll move on to damping. The first two models do not include damping. However, in the bonding V2, the coefficient of restitution can create damping-like effects. Without dedicated damping, the particles can oscillate for a long time after contact. The fibers bonding model damps the relative linear and angular velocities between particles in contact. As seen here, the fiber can oscillate, but you can adjust the model settings to achieve a more realistic fiber behavior. The bonding V2 model uses the contact radius to search for neighboring particles and establish a bond when their contact radii overlap. If the contact radii between two particles no longer overlap, the bond will break even if the applied load has not exceeded the predefined breaking stress. Therefore, the contact radius plays a critical role for this model. The linear elastic model and the fibers model use the preserve contact functionality. This means that particles do not need to be in physical contact for a bond and contact to exist, and the bond is maintained until the failure parameters defined in the contact model are reached. Next, bond displacement. Here, we can see an elongated particle rotating. For the contact model shown, the bond forces are calculated iteratively at each time step. When we stop rotating the particle at the same position where we started, and without any particle failure, we can observe that the elongated particle has deformed. This shows that bond positions may creep under repeated loading in the same direction, a behavior typical for this type of scenario. However, this does not occur when using clumps of particles. With the fibers bonding model, as we rotate the particle, absolute forces are calculated rather than incremental forces, making it more accurate for scenarios involving repeated deflection. As a result, the elongated particle returns to the same position at the end of the rotation, and this is because the model is more accurate for absolute displacements compared to incremental relative displacements. Finally, let's look at the input parameters for each bond model. First, the linear elastic bonding model is a simple model, where only the normal and shear strength of the formed bonds are required, in addition to the particle material properties, such as the shear modulus, which is used to calculate the bond stiffness. The bonding V2 model includes more input parameters, such as normal stiffness and shear stiffness. The bonds are formed according to these parameters. The fibers model is the most complex of the bond models. At the top of the input panel, you'll find the elastic parameters. These inputs are used while the bond remains within the elastic range. Below that are the bond failure parameters, which you can adjust according to your application. Here, you can select both the failure criterion and the post-failure behavior of the material. At the bottom, you'll find the buckling options, which are particularly useful when simulating fiber-type materials. This concludes the EDEM bond models comparison lesson. For more information on each individual model, please refer to the EDEM documentation, the e-learning contact models course, and the online EDEM tutorials.